Okay, good morning, everyone. So we will start our session. So this session is designed to go through the Energy Frontier Vision Report. Alessandro will give this talk on behalf of the conveners, and then Vladimir will talk about the Accelerator Frontier Report Vision, and then we will have time for discussion. Again, the idea is to have, I would say, discussion sort of which in depth will sort of check ideas, provide feedback to the conveners if any sort of modifications to the reports are needed. But so suggestion, we will go through, we are on Zoom, sort of, we might have some questions from Zoom. So the idea is that we will go through Alessandra presentation about 20, 30 minutes, and then Vladimir will talk. And then when we see the full picture, because look, as we know, sort of, we are very closely connected. We couldn't do physics without colliders, and colliders need sort of feedback as sort of what we need to do the physics. So then we will have a discussion. Please wait for the mic. So I will, and I hope that everyone will be able to ask questions. So with this brief introduction, Alessandro, please.
Thank you, Dimitri. So yeah, I'm really looking forward to this session. So I'll try not to speak for half an hour. So we have time for discussion. So I'll try to be brief and go to the point of what is relevant for the discussion between Accelerator Frontier and Energy Frontier. And also don't want to preempt much the session we have tomorrow, which is also advertising now. We have a session tomorrow for the Energy Frontier where we'll go through the details of the physics. We have several presentations and on the physics as well as the vision. So what I will do here is a bit preempting that discussion, but I want to preempt too much. So I will invite you to come tomorrow, especially to discuss in great detail the physics that is in the Energy Frontier report, as well as the topic group report of the Energy Frontier. So I'll try to be brief, but let me first introduce what we are trying to do in the Energy Frontier. So we want to explore the TeV energy scale and go beyond. And we have several big questions we want to address in various fields, which touch other frontiers as well. So we have the evolution of the early universe, which also touches the cosmic frontier, matter-antimatter asymmetry, the nature of dark matter, origin of neutrino mass, again, a strong link with the neutrino frontier, the origin electroweak scale, and origin of flavor. But also history has told us that the exploring the unknown is a big driving force, and many discoveries were unexpected. So we have to explore the unknown as a major driver for the Energy Frontier. And we have several probes in the standard model and beyond the standard model to address those questions in the electroweak sector, in the Higgs sector, in the strong interaction sector, as well as direct probes for new physics. It can be dark matter, can be new particles, interactions, as well as new symmetry in space and time. And we use several signatures, final states, and model or model independent signatures that we try to address those big questions in the realm of those probes. So let's go now to more the topic of this presentation. The success of the Energy Frontier really relies on new developments of accelerators, as well as the technologies. So really, we depend on this. So we really promote development in accelerator realm, as well as in instrumentation. More on a practical side, we have two approaches in the Energy Frontier to look for a new physics beyond the standard model. One is to look for known phenomena, understanding the greatest possible detail, look for the deviations from our expectations. And in this context, E+/-Higgs boson factories are play a big role. And of course, these Higgs factories not only produce Higgs bosons, but also factories of many standard model particles. And we want to study in great detail those particles. But for this, we need high luminosity, and also we need to set the energy of the machine very accurately to reach the right precision in the right channels of physics. But also we have to do direct searches of physics beyond the standard model at the Energy Frontier, which means multi-TeV colliders. And for this, we need very high energy colliders. In addition, we also need high luminosity, though, because we need to also probe regions of phase space that are not accessible by the LHC. And for this, to reach such precision, we need high luminosity as well. So in this diagram, which probably those who were here on Sunday have seen this before, is also in our Energy Frontier report, we try to depict this two-tier approach that we have in the Energy Frontier. So if you take a schematic of plot of a mass scale that we can reach and the coupling of BSM to standard model particles, and we put the LHC right here, roughly in the middle. With Higgs factories, we try to reach low couplings. And for this, we need very high luminosity. And these are inaccessible by the LHC, this kinematic region. With high energy collider, we want to reach the highest possible energy. And for this, we need multi-TV collider. So the approach that we take is may seem a dichotomy. We may seem that we either have high energy colliders or Higgs factories, but really what they explore are different kinematic regions of phase space. So both are needed. The question is, what can we afford? What can we implement? And what is the consensus behind those machines? But we need definitely energy and precision at the same time. And this very briefly is a quite detailed diagram, but it's pretty much the same as before. But I want to highlight a few things to this audience. Again, here you have a mass scale and the coupling standard model. If you have Higgs factories, you can set limits here, mostly low mass scale, but can go very low in couplings. But also you can set limits indirectly, not only by direct production of new particles. And then you have these diagonal bounds, and depends how precise you are in your measurements, the bounds can go down, down, down. So this is what we're trying to do with indirect measurements of new physics. And the LHC is here, and probably slightly high couplings, but reach in the middle of the mass scale. And then with the high energy colliders, that we can push to the high mass scales with direct limits on new physics. So this is two approaches. One direct conclusion of this slide, we have direct measurements as well as indirect measurements. Both are complementaries and very important. So what machines now? We have two main categories of colliders. We have hadron colliders, which can reach typically the highest possible mass. So they're really high energy collider typically, but they have large backgrounds. They need performing triggers. And they are affected by the proton structure. So they're not very clean machines, but these are notoriously as discovery machines. And they mostly are affected by quark and gluon couplings. We have lepton machines, which are much more clean environments with very low backgrounds. They can use polarization of the beams to reach the channels and enhance cross sections of a physics that we are mostly interested in, but are limited in the mass reach for direct production of resonances and new physics. They're mostly sensitive to electroweak couplings. And of course, we have circular linear collider. They have pros and cons. So the circular collider can reach high luminosity. It can allow several interaction points, but affected by the synchrotron radiation. With linear colliders, these colliders can be upgradable. So we can start a short linear collider and upgrade it, which is very useful for budgeting. But also, as I said, can use polarization really to access the channels and the physics channels that you're interested in and increase the cross section. And typically cleaner with a lower power consumption, but also allow us one single interaction point. So here there are some graphical representations of the major projects are on the table. But in the Energy Frontier, we try to standardize the studies, put in some benchmarks. So we have two different tables, one for Higgs boson factories, typically up to 1 TeV, center of mass energy, and then another set of table for high energy multi-TeV colliders. But first, let me say high lumen LHC is a category by itself. It's the most important projects we have now, and we're all behind the high lumen LHC. But also we have other projects for the future. We have ILC and C-cubed, CLIC, CPC, FCCE in the realm of Higgs boson factories. And for multi-TeV collider, we have high energy LHC, FCCHH, SPPC, LHC, SCC-EH, click, and also the muon collider. The muon collider is in both categories in case of Higgs boson, but also as a multi-TV collider, which is maybe the favorite option so far. In terms of timelines, we really stick to the timeline given by the ITF, so in the accelerated frontier. And here you see the parameters of central mass energy, working points that we use in our studies in the Energy Frontier report, the polarization, and the integrated luminosity. And one thing I just want to advertise again, was advertised already a few times before, but we had a series of Agora, which were colloquia, very highly attended by many people, and they're very, very instructive and very useful. So if you haven't attended those, I really invite you to go to those links, listen to the recordings. They're very instructive and very useful to understand the pros and cons of our colliders, the feasibility, the challenges, the cost, etc. So let's go a bit more in the physics side. I don't want to preempt much what we'll discuss tomorrow, so I'll just give you some highlights and the flavor of what is in the report without going into many details. So first of all, the Higgs boson is a new particle. Many people think actually is a beyond the standard model particle. So it's something we have to study very accurately because it links to many other topics in the energy frontier: origin of masses, flavor, naturalness, electroweak symmetry breaking. So it's a paramount important to study the Higgs boson properties as accurately as possible. And this will tell us more about the electroweak scale. And by studying the Higgs boson, also can get information about what we call the ultraviolet physics, the high energy physics. Can tell us about the Higgs potential, why it has this shape, insight on flavor, but also flavor physics, and also gives insight on the Higgs boson. And also top quark is very important by itself, but also in relation with the Higgs boson. So ultimately, this is motivation for Higgs factories. And here there is a flavor of what we can do at future colliders insofar as Higgs self-coupling. So here you see the highly luminous LHC reach for direct di-Higgs production, uncertainty, indirect, and combination. So you see just from this table, they see it's very important to have high energy as much as possible to really improve the precision on di-Higgs. Indirect measurements are sensitive, but they don't go much beyond what we can reach at the LHC, with some exceptions. For the FCC-EE, for example, can go to 33%, and for interaction point, 24%. But really the biggest gain is when you go with direct production. And then you can do that in several machines with linear colliders, E+E- at high energies, or hadron colliders or muon colliders. And this plot shows the improvement we can achieve at future colliders in understanding the standard model and testing really the standard model with great accuracy. So you see here the precision of the Higgs mass is so good that we don't see an error band on this plot. And this is the top quark mass. And you see our current estimate of prediction from electroweak fits for the top mass and the Higgs boson mass, and what we can achieve with future collider. And you see how much E+E- collider can achieve, especially circular colliders in this case. But we can do much more beyond the Higgs boson. It's our responsibility to look for physics beyond the standard model, and we can do it in several ways, mostly two ways. One, looking for model-dependent signatures, and this is quite clean because it allows us to really connect the ultraviolet regime with the signatures that we experimentally can detect. Allows us also to compare experimental results across experiments. But also we have to go beyond classical paradigms, look at new models, and there are many in the last few years that came up, like long-lived particles, field interacting particles. But also we have to conduct, as much as possible, independent searches for new physics in a model-independent way, as much as possible. This allows us to probe the signatures that we have available experimentally and see if there are deviations which are not captured by specific models. And also, I will highlight in the next slide, there's a strong complementarity between collider physics, cosmic experiments, neutrino experiments, and rare physics processes. This is what I'll try to illustrate in the next couple of slides. First, let me give some examples of searches in the energy frontier. Here is an example of a heavy boson Z prime model. It's a universal Z prime. And here, again, we go back to the original plot that I showed you at the beginning when you have the mass scale of new physics and the coupling. So this is kind of, we go back to the original schematic now in a concrete example of setting limits on a concrete model, which is a Z prime. And you see here this high Lumi LHC exclusion region, and you can exclude more and more at the higher the energy at linear collider, E+Manus, circular colliders, as well as the muon collider. And you see here this curve is where you have direct detection or the direct production, so you can exclude a significant portion of a phase space by looking for direct production of Z prime, or with these lines where you have indirect detection. So you can set limits indirectly on new physics. And here you see again in the parameter space of mass and coupling, the exclusion that you expect from future colliders. You see many. Again, there's a direct and indirect limit settings that are very much complementary. So we try to explore both as much as possible. And in this slide, I want to show mostly complementarity between different physics, the collider physics and other experiments. So here in the dark matter, and this is a WIMP example in the case of Higgs-SINO, you see the reach of various colliders compared to indirect detection. You see that we are very competitive, but also complementary in the approach where we study and look for dark matter. Similar here, we have the mass, and here the muon mixing, and you see here how much we can reach in mass scales at collider physics compared to other experiments, and you see CODEX and Methuselah, Dune, SHIP, etc. So really, at collider physics, we are complementary in the kinematic region that we can cover. We can go to very high mass scales, and these kinematic regions are accessible by other experiments that are non-collider experiments. Then we can also do a lot of QCD studies. And one aspect which is very important is the study, quite detailed in the Energy Frontier report, is the strong coupling constant. Especially at E+Manus collider, we can reach great precision on the strong coupling constant. Now we have a precision of 0.8%. We can reach 0.4% in a reasonable short time scale with Higgs factories, especially FCC-EE, but also we can reach 0.1%. It is very important because it's not only fundamental parameter of the standard model, but also any deviation in the strong coupling constant can give hints of new physics, not only in the parameter itself, but also in the running of alpha S. But also there are many other studies we can do future colliders, like understanding better the jets. And this also in relation to other experiments, for example, the electron ion collider that is the next big project in the United States, can really help us both understanding the jet universality, as well as part and density functions. So the really complementarity within the energy frontier, high energy physics, as well as nuclear physics. So that was a very brief excursus of the physics. But again, I don't want to preempt the discussion we'll have tomorrow. So please come to Energy Frontier session tomorrow, and we'll go in great detail on the physics. Now we shift to the Energy Frontier vision, and which is relevant for also the Accelerator Frontier. So in a nutshell, is of paramount importance for us to complete a high-LUMI LHC program. We want to start now a program for detector R&D for Higgs factories. We support the construction of a Higgs factory as soon as possible, but also want to ensure long-term viability of the field by developing multi-TV collider. It can be a muon collider or a hadron collider. It's important to start now the R&D to allow that long-term viability of the field. It's a nutshell. Now I go into more details. So the Higgs boson discovery about 10 years ago, plus a few days, really opened up a new scenarios for us, and it's our responsibility to understand the Higgs boson as much as possible. Not only because it's a test of a standard model, but also it's a way to explore new physics. In fact, people believe the standard model, the Higgs boson that we see, is maybe a new physics object. So it's really important to study as much as possible. But also we need to look for new physics directly by searching for BSM signatures. And as I mentioned, collider physics really complementary, allows to reach kinematic regions that are not accessible by other experiments. So hopefully I convince you about that. And we have to develop a plan which for immediate future, intermediate future, and long-term future. So the immediate future is the high-LUMI LHC. There's no question about that. We want to provide the strongest support for the high-LUMI LHC, complete its physics program. We support the detector upgrades. We support the operations of the LHC and the physics analysis. And we also support the construction of auxiliary experiments, which are discussed now, which are complementary in terms of each of kinematic phase space with respect to the central detectors at the LHC. But also we want to prepare now for the future, for the next collider, which is the intermediate stage. So we need to prepare for the future now. And this is, we're going to intermediate future plan. The intermediate future plan is an A+/- Higgs factory, linear or circular collider. There are compelling reasons. Physics case is very strong. I do not go into detail for lack of time. Here there are some examples, both in the Higgs boson sector, in the BSM sector, standard model, QCD sector. There are various proposals for A+/- colliders, linear and circular. All of them have a strong physics case, and there's many commonalities, but the most important message, and we want to realize at least one somewhere in the world as soon as possible, meaning in the time scale that is relevant for early career physicists now. I think this is a strong message we want to get across. We do not want to wait.
What is that?
Let's.
Early career physicists has till they're 60 or 70, or? Sorry.
Let's not discuss ages now, but okay. Let me conclude. Then we go back to discussion. Another important point in the intermediate future is that we have a robust investment in detector and collider R&D focused on Higgs factories and multi-TV colliders. We don't want to lag behind. Again, is in preparation for the future of the field. Long term is a multi-TV scale collider at roughly a 10 TeV parton energy scale, which means it can be hadron colliders roughly at 100 TeV energies, or a muon collider. The physics case again is very strong in both cases. I don't get into details, but they can really probe naturalness, can probe the mechanism behind electroweak symmetry breaking, will search for new physics in a model dependent way and a model independent way. Will be exploration machines. there are complementarities and similarities between the two types of colliders, hadron colliders as well as muon colliders. Of course, proton colliders is more access more the color states and compositeness. Muon colliders relies mostly on vector boson fusion and low backgrounds. But the message is both colliders are limited by the technology now. So we need to have a vigorous R&D program to allow the development of the critical technologies to enable those colliders in the future. And there are also opportunities for the US. Of course, this is a worldwide field. We are embedded in international collaborations, and the US as well as international community of scientists have thrived in this international community which is represented here, many nationalities and many languages. So this is, again, something that has to continue very strongly in the future and has to be supported. However, in order to have the US be competitive in the future, we have to have a robust R&D program where the US can maintain leadership and be competitive with partners elsewhere in the world. And in some cases, we're lagging behind in this R&D. So this has a vigorous R&D program in various sectors to maintain leadership and maybe strengthen the leadership. But also there is a new interest in the community and the ambition to bring back collider physics on the US soil. And this is not only for the benefit of the US community, but also for the international community. Talking to people elsewhere, there is a strong sense that strong collider physics in the US will benefit overall the community, as well as Tevatron operating together with the lab was really an enrichment for the community and was beneficial for both the CERN physics program as well as the Asian program as well as the US program. So more concretely, we need to proceed in a multi-pronged approach to adapt to international contingencies, especially now in this difficult political and geopolitical situations and constraints. However, we have some attractive opportunities which should be considered. One is a plus-minus collider based in the United States, or in the future, a muon collider in the United States, or try to exploit as much as possible the Fermilab site, which we call a site filler. These are new, bold projects which have inspired several people. We had 40 contributed papers on muon colliders. So this is a new ideas which I think enrich our field and inspire on long-term young generations, and also new ideas like C-Cube that came in more recently, but this is an idea which has been there for a while. So these are inspirations that we want also capture to make sure our field remains young and vital. And with this, I conclude to say what are our resources asks and the timeline. So going back to the immediate, intermediate, and the long-term plans. So starting in 2025, in a 5-year period, the highest priority is a physics program of high luminosity LHC, including auxiliary experiments. We want to establish a targeted E+E- Higgs factory detector R&D for the US participation in a global collider. We'll develop an initial design of a first stage multi-TV scale muon collider in the US, pre-CDR. It support also detector R&D towards multi-TV colliders. Then in the following 5-year period, starting from 2030, again, we want to have strong support for LHC physics program, which will continue in the mid-30s. We want to start construction for any plus-minus Higgs factory, wherever will be sited. And we want to demonstrate principal risk mitigation and delivery CDR of a first stage TV scale muon collider. On the longer term, we'll have to wrap up the high luminosity LHC program, so it still has to be funded towards archival measurements. Want to begin and support the physics program for the Higgs factories, demonstrate the readiness of and construct delivery TDR for a first stage TV scale muon collider, and again, ramp up strongly in a vigorous way detector R&D for multi-TV collider. And again, to conclude, we really recognize the importance of Accelerator Frontier and the development and R&D in Accelerator Frontier. So we strongly support your enterprise, and we should maintain our strong interactions and collaborations moving forward. Thank you.
Thank you very much, Alessandra. So the proposal is that we will probably go through some discussions because we have your slides here. So, and then Tor will talk about the Accelerator Frontier problem. So I'm sorry that, look, there is not, it's the first meeting at SNOMAS where the room is overfilled. Look at least this. So I think we're doing pretty well, yes, sort of. But there is one more chair here if you really would like, to come. And we do have people on the Zoom. So please wait for the mic because there are quite a few people sort of trying to listen. So please raise your hand. I will give you the mic, and then look, Alessandra will try to answer.
I'd like to make 3 comments. Comment number 1, CERN has taught us that you have to build on what you've got. Point number 2, the SSC has told us that starting from scratch is folly. Number 3, you can't build a 100-kilometer thing in the mountains. Therefore, there's only one place that makes sense and only one program that makes sense, and that is to revive the super collider at Fermilab. Essentially, it's the FCC 100 kilometers, doubled magnetic field, center of mass energy of 80 TeV or so. And it's just very natural to do this at Fermilab.
Thank you for your comments. We have Lisa.
Thanks for the talk, Alessandra. I'm really surprised by your.
Seems to be working. Yeah.
Sorry. Yeah. So I was surprised by your comment on the 3rd bullet about evaluate continuing the HLHC program. Can you elaborate on that?
So which one?
You say evaluate continuing the HLHC
No,
program
but
at 2035.
well, this is
So
also,
in principle, we still have 5 more years of data taking at that point.
yeah. So the message is we have to exploit as much as possible high luminosity LHC, and we have to at least collect 3 inverse autobahns of data. Depends on how point in time that will be. So we exploit it as much as possible. But I see. I mean, actually, once.
Okay. Meenakshi.
Okay, so instead of support continuing would be better.
Yeah.
Yeah, because what we hear, and I have, of course, it's all.
Yeah, on the.
Okay, what we hear is that CERN may be considering at the highest levels to turn off after 1 inverse after Autobahn. There've been comments made in various places about that in the open by very important people at CERN, let me put it that way. And we are worried about it because the Dye-Higgs program really needs the full luminosity, and that's what we are in for. So we would really like, and if some other hints show up for something else, then we have to think about even going more above 3 inverse Autobahn. There is the 4.5 inverse Autobahn scenario too. So we should keep it, because after this, there is going to be a long gap for any physics.
No, but the message is that maybe
Just one at a time.
rename. They would reward and evaluate with something else. Support. Yes. Yeah.
Yeah. So is this meant to say evaluate prolonging the HLHC program? Or stopping?
No.
This sounds like stopping. Okay.
It's not stopping. It's try to exploit as much as possible. That's
Okay. Okay, good. Look, okay. Look, Frank, please look, let's listen for Frank.
So I have a comment directly to what we just discussed. Of course, also with my hat as the chair of the LHCC. Clearly, I think it's important to get a message of how we see this, what the program should be, right? We are discussing very expensive upgrades for LHCb and ALICE that are absolutely pointless if we turn off, right, at 2035. right? And in addition, you could also argue that many of the phase 2 upgrades we are now struggling to complete
Yes.
become pointless if we turn off after one in West Autobahn, but they're just not worth the investment. And I think it's important that there's an opinion from the US on this, right? And then maybe a more, well, I don't know if it's a provocative question or so, right? I mean, you showed the various ideas of having a domestic collider program, which I personally would find absolutely fantastic. But how does that tie in with, so how do you see this decision, right? I mean, at the moment, we just increase the zoo of possibilities, which just means we get even more stuck than we are already with waiting for Japan, knowing that it will take a while at CERN, waiting for Dune to complete, right? Also, with this point of the younger generation, right? I think we cannot wait until 2030X to know that there's a future, right? So how do we get there?
So let me
it's
first.
clear that these things can only happen once resources are there, but the decision somehow.
I think we discussed this collectively also in the discussion session. Let me see, on your first point, we reword evaluate. Evaluate for us as a positive meaning, not the negative meaning, right? So that's to make it clear. So we definitely support that. So that's make clear. On your question, I think we see, as put in the slides, an opportunity for the US, not necessarily a driving force to say we need to have a collider in the US as high priority. I think this is an opportunity, this is opening up in the next few years, and we have to be prepared for that. And I think there's definitely consensus in the community. There's an opportunity that was not there before for technical reasons, as well as generational reasons. And it's probably about the right time now to bring that to the surface, this ambition. And I think so to see it as an opportunity. So it should not be as a competitor, it should be just seen as an opportunity.
But other, yes, please.
I was wondering about the far future. I mean, you mentioning the PP and the muon collider, but not plasma wave field, for instance. The other things that have been discussed in the accelerator frontier, is that conscious from the energy frontier to not also support development on?
So this is maybe more a question for the accelerator frontier.
I mean, it's your input to saying
Our
physics reasons. Yeah, the physics reasons for not mentioning that. Right?
I don't think there is a strong physics reasons. It's mostly technological reason at this point. But I think definitely I would say, then Meenakshi wants to speak, but we definitely support the R&D very strongly. So the R&D should continue because I think it's very important for the future of the field. But
isn't it then important that that is mentioned in the?
We mentioned the R&D, but this is part of AF report as well. So in terms of physics, there's no strong motivation, but I think it's mostly driven by the technology of the accelerator frontier.
I slightly disagree, because from the physics point of view, there are other issues with beam parameters and stuff, which we need to understand. So we, in the entire 2 years, have really did not get any beam parameters for which we could use to actually do the physics. So we really don't know that the physics impact is exactly the same. So I'm going to make a plea to my plasma wave field accelerator colleagues to please give us, even now, right? You know, SNOMAS will end, but we will continue, our interest continues, and give us those beam parameters, and we will try to bring it. Maybe they're on the same footing, or maybe they're different. And from what little I understand, there may be differences.
That is right, but I think we agreed it's a technological challenge at the moment. Yeah, yes.
And invent some new name for this, C-Cube or look, muon collider, nice name, brief. Yeah, so you need a name, yes. Sir. So look, who else? Oh, please, yes, please.
I think
No.
Okay. Great. So thanks for those comments. I think
Can keep it closer, just wait.
thanks for those comments. I think you know, I was thinking along the same lines that it would be nice to see at sort of a high level what you did have in your talk, right? Sort of the accelerator R&D program, because there are nearer term accelerator technologies that are, you know, as Meenakshi very correctly pointed out, right? We have beam parameters, we've done calculations for them. Very appropriate to have those you know, highlighted, right? But at the same time, there are technologies developing, right? And the energy frontier vision is what allows us to motivate those, right? And so I think in particular, when we talk about, this is not so much to talk about in the report, where we talk about signatures and things like this, I think Patrick Mead did a beautiful job of saying, this is what we've evaluated, but leptons are of interest. And if we could pull in some things like that and maybe some general interest in future technologies, I think that would help. And then absolutely, Meenakshi, we take seriously your comment. We've been trying to do that, made progress on that. This SNOMAS, historically, we have been only a technology R&D program. We do now have parameters. They are not at the level, certainly, of other colliders. But we are working towards that and actually starting to work with some folks in Energy Frontier now during SNOMAS and Theory Frontier, including Patrick and others, to start to do this calculation. I absolutely acknowledge your point, and that is the progression that we're hoping to support.
Cameron, thank you very much for your comment. Any further, Søren?
Yeah, just maybe it's a contentious area, but on the slide where you compared the various colliders, you had the Muon collider and the FCC AHH, and when I looked very cursorily at the numbers, they seem to overlap a lot. Can you say something more about the physics pros and cons, those two?
Yeah, so we explained this in great detail in the report, and Energy Frontier report, as well as in the Toppler Group reports. So here we don't go in much detail. In many aspects, they have similarities in the physics reach, but the devil is in the detail. Of course, it depends on the channel you're looking at, BSM or standard model. So there are similarities, but also complementarities in the physics reach. In terms of detectors, there are definitely similarities, which come also from benefit from the development for high Lumi LHC. Although Muon Collider is a lepton machine, the beam background is so high that really benefit from the advantages coming from tracking and time detectors for the high Lumi LHC to reduce the number of channels because they need a very high occupancy. Whereas the hadron colliders have similar problems, but also have problems of very high fluences, high radiation levels. So there are both complementarities and similarities in both in the physics as well as in the detectors, and both cases really benefit from the experience from high Lumi LHC. The different machines, the hadron colliders are mostly gluon colliders. So really it's QCD-driven physics, whereas the Muon colliders at a very high energy is mostly a WW fusion machine, which turned out to be very useful in the last few years studies of SNOMAS to really reach high energies, and also has benefits in terms of power efficiency. So we can talk for a long time about it. I think the Energy Frontier reports try to summarize all these discussions, both in terms of physics as well as at detector or accelerator level. So I invite you to maybe have more detailed reading of the report, and then we can discuss on specific questions in more detail later.
Okay, thank you. So now we have comment.
I have a
Vladimir.
bunch of comments, but very concrete and relatively small. On this particular slide, we go in reverse order. The 5-year period starts in 2030. Second bullet, third bullet is demonstrated principal risk mitigation delivers CDR. In our world, CDR has certain meaning, and DOE usually asks teams to prepare CDR. It's not that anyone from this group can write a CDR and deliver. It's not happening this way. I think between you guys, Dmitry knows DOE system really well. So could it be either a reference design report, accelerate the reference design? ERIC, for example, in 2014 had very nice CDR, but they called it ERIC design study. And CDR for E-electron collider is just delivered last year. So you see there was a CDR, what we understand as CDR, but it was named differently. So
this is a clash of terminology between the US and
right.
international
And
community.
I think we should clear that up. On the previous slide, slide 24, when you turn, cursor should be on the slide, and then slide changer works. Yes. 3 bullets, attractive opportunities, right in the middle. A US cited linear collider, ILC/C cube, and third bullet, exploring other colliders to fully utilize Fermilab site. Does the first bullet mean that these are not Fermilab cited colliders? Could be. Now just tell us what's in your mind. Okay. Okay.
Can you give me the microphone?
Oh, sorry.
For example, ILCC cube could be elsewhere.
Mm-hmm.
And also some other, since Fermilab is very busy, right? And we haven't really negotiated with them or talked to them.
Mm-hmm.
There are other labs which could possibly step up to take ownership. And this is a discussion which should happen. We can't automatically think that Fermilab can do everything given the dune bulge.
My concrete
That is
proposal.
my personal opinion.
My concrete proposal would be to combine units, points 1 and 3 into one sentence, like US sited linear plus or minus collider, ILC/C cube, potentially on Fermilab side. Disagree? Okay, fine.
Okay.
Good. The previous slide, 22. 22.
I don't know. What number is it?
One more. There is some statement somewhere about excellent signal to background in a muon collider. I don't know. Is it really correct? Is it slide 22?
I'm not sure it's here. On the muon, I mean, there was a sentence.
Yes,
in-
yes. Muon collider can take it. It's a second
yes,
bullet. Take
yeah,
advantage of
yeah.
W fusion and benefit from excellent signal to background. I think it's only compared to HH collider. It's excellent signal to background.
Yes.
So muon collider is known
because
to be
this bullet point is
quite messy.
we're talking about you talk about the beam induced background. I agree, but this is kind of comparison with
No. Again,
it's the physics background they talk about, not the beam background.
So just to deal with that, a word like excellent is if you're doing a comparative statement compared to the better,
yeah.
from better.
Yeah.
yeah.
No,
Okay.
and also maybe we should distinguish this. We talk about physics background, not beam induced.
But it's not
background.
written there, right?
I
So
agree. It just has to be expanded the sentence.
Yeah, you're making.
Yes, I agree. Yes.
Thank you, Vladimir. Look, I would agree that some wording
Yeah.
after you get
Yeah,
feedback,
no, it's good
you
point.
might
It's-
improve a little bit. Oh, thank you. You just have to turn it on somewhere. There should be, yep. Rotate.
Is it on?
I think so. Yeah. No, it works. It works. Yeah, it works.
Okay, well, first I was on the E+ E- Collider forum, so thank the conveners for inviting me to participate in that. And looking at the energy frontier, basically there are 3 collider options. There's the HH collider option, there's muon collider options, a Wakefield accelerator collider option. I would just encourage, like in our report, we explicitly call out the Wakefield accelerator is an option. These are very long-term. If it goes along according to your vision and FCC were to get funded, that will probably be, the dominant machine for many years to come. So keeping both of these options on the table is just, is a sensible thing to give us that. And it is a longer range option than muon collider potentially. But I think having both of these options, since there's only 3, to leave one out just seems like a discouragement of the Wakefield, support of the Wakefield acceleration research. So I think it wouldn't be much to add
I see many people want to
to
answer this
keep,
question.
yeah. So this is maybe oh, go ahead.
Let's start with.
Yeah, I think there was a very clear statement that the physics has been evaluated for a muon collider, and that I mean, in general, I would agree with you that one should say lepton and not make a technology decision at this point. Although I also have said many times that I think the Wakefield accelerator has to show that there is a potential there that I don't see yet. So they have to show that's a real potential. But I would not suggest excluding it at this stage. That said, you have done detailed physics showing that a muon collider works, and you haven't done that for the equivalent of Wakefield. And I would be very explicit about that. We know, this looks good. The other we know
Exactly.
nothing about.
So I think our view is that we need to continue the R&D. This is very important long term. However, elevating this to this level, we are uncertain at this moment. We don't have enough feedback from that community to elevate this to a explicit recommendation to put the same level to ILC, click, and so on.
And possibly a Wakefield collider, right? So you believe the muon collider is a real option and possibly a Wakefield collider.
I think
Yeah, I think you're absolutely, first of all, I think you're absolutely right. And I don't think any of us are proposing to put it at the same level that things that have been evaluated, back to Meenakshi's comment, and I'll hand to you next. And something like that, and possibly or general or R&D or something of that nature that opens to basically encourage and let us work with you in the future to come to that point is what we're hoping to work with you on. But by the way, I want to say, I'm very happy to see that highlighted for the Muon Collider, right? It was a terrible mistake that got canceled. So we want to avoid crossing with that in a respectful way.
Okay, wait. Oh,
Something so that's a little bit.
is it on? Is it on?
Is it on?
You have to rotate this knob.
I have to rotate it. Is this better?
Yes.
Yeah, so basically there are two bullets which in our vision summary, which we actually call out, which is not here. I'm reading from the report, which says that we have a whole section which says, or paragraph, 2 paragraphs, literally that EF community strongly supports the accelerator frontier and its resource needs and requests to establish an E+E- Higgs factory program, start R&D for EF multi-TV colliders. And I think your request is in there.
Very good. Vladimir, do you want to?
Sorry, very quick. So I think this is very proper language, and moreover, I believe at this stage, Energy Frontier summaries and Energy Frontier report is not right place to bring up too many options.
Yes.
Right. So in Accelerated Frontier summary, we specifically mentioned that we see that ahead of us there are a number of years when our community should provide self-consistent set of parameters just to start discussions about feasibility of these Wakefield accelerators in the future. But for Energy Frontier vision, especially these high-level slides, I think it's probably not the right place. Sorry.
Very good. Let me just give it to Sergio.
Yeah, so a quick comment with regards to bullet 2. It's my recommendation, but I suggest maybe reworking it a little bit. It's covered by the window, so it's a little bit hard to read, but a PP collider has, so I agree with the first sentence. A PP collider has easier access to colored state. I think I would agree with this statement. Compositeness studies, I mean, there's a number of compositeness studies, so it's a little bit of a generic statement. I believe depending on exactly what you have in mind, whether it's an excited quark or something else, there are cases where muon collider is superior or FCCHH is superior, so it's not a universal statement. The other thing is, I found a little confusing, is that in the same sentence, there is a statement about taking advantage of VV fusion, which is, I guess you're referring to Higgs and talking about the Higgs, VV production of the Higgs, and therefore, you can benefit from high rate, and therefore you can do precision measurement there as well. But since it's coupled with BSM, it's not clear whether this refers to the Higgs, to the BSM, and whether actually the excellent signal to background refers to physics background or instrumental background, right? So it's a loaded sentence, and there are many messages.
No, but
and
this sentence is just a summary to fit in one slide.
Right.
So as you well know, the Energy Frontier report really goes in great detail explaining this. So this is just one way.
Right.
To
I think this
summarize.
is maybe if a sentence is artifact of maybe previous slides, or I don't think I saw this exact sentence in the report. Maybe do you think it is?
No. It's a summary. It's a summary of. It's a summary of several paragraphs in the F report.
Okay.
So
okay.
Yeah.
So maybe for the slides, maybe we should rework it a little.
Yeah.
Very good. So look, we will go to Patrick first. Yeah. So because he's kind of.
So, I mean, from the EF report, I mean, I obviously understand everything going on here. I was curious for the EF-AF kind of combined report. We have this sense of urgency for the R&D program for the high energies, whether it's HH, muons, Wakefield, because we need to have this path. One thing that's definitely not in the EF report, because it's EF, is this also connection to NF, where we just had this NF-EF cross-frontier session talking about how some of the plans at Fermilab for the booster replacement, et cetera, those can influence the path that we're going on. So I don't know whether it's going to go in the EF-AF or maybe something higher level, but I think it's important, just like we're saying, if we want to have a path for the future, we need R&D now. But we also need to think about our choices we're making in other frontiers to give us the best chance to have the most options in the future.
Yeah,
good point. We have over there. Do you have? Can you give mic, please?
Is it on the microphone? Tap it.
Yeah, now it's on. On 25, so the resource and timelines there. I was wondering about the Higgs factories.
Yeah.
Of course, for the Higgs factor, it's the US is not really deciding the timeline, right? I mean, I'll see.
Closer to your mouse.
Sorry. So now it's quick. Okay,
Yes, nice.
good. Yeah. So, I mean, for the plus or minus Higgs factories, the US is not really deciding the timeline, right? For ILC, it's up to Japan, and for FCCE, it's up to CERN. And but here, nevertheless, you're saying that in these 2 steps or 5-year steps, we're going to do this and that, and that's not necessarily so that.
I'm not sure I fully agree with you. So of course, US is a very important partner in all these projects. And I would say the intellectual participation as well as financial participation of the United States in all these projects is critical. So although the decision may not come directly from the United States have a big saying in what collider will be next and when. So I think I wouldn't downplay the role of the United States in shaping the field as well as the timescale.
Okay. No, but my point is really with this way of writing, it is sufficiently flexible to actually react to that. Yes, the Higgs E plus minus Higgs factor is going to be realized somewhere globally as it says, but not really fitting into that timeline. So you can.
Maybe actually want to.
Yeah. Look, there are quite a few. So did you finish yours? Okay. Look, I just want to go. Look, why not we start?
Yeah, Meenakshi had showed this slide in the C-cube discussion, and I questioned it as well. I worry that putting a very aggressive timeline out there can be detrimental. Now, I also understand that you want to keep enthusiasm going, but it really, I mean, there's all sorts of things that come into play. I don't think the optimistic, as I understand the optimistic timescale for ILC, you begin construction in 38 now. So that's assuming that it takes you 2 years to get funding together to do both the pre-lab and the construction project. There's 4 years of pre-lab and there's 8 years of construction project. And both of those are documented. So you're talking about 14 years from now, time early.
I'm not sure. Well, okay, we want to answer first. Go ahead. Okay.
Yeah, so first let me, I didn't get the name of the gentleman who made the earlier comment. I have to say that, and I agree with Alessandro, US is a big financial partner in any of this. And if we don't start talking to our funding agency about letting them know what we support or don't support, that is going to be a big thing. CERN could decide to go ahead with something, but if the US doesn't have the money to support it, I don't think so that's happening. And to answer to Tor, I also hear, and we should all ask Fabiola when she's here in the next few days, that CERN would like a commitment for the tunnel digging from the US as early as 2024 or 5. If that is the case, that needs to be clarified, as I said. And if that's the case, then, and if the US commits to that, I don't know what the process would be. We've never figured out how to do civil engineering elsewhere. That would be a complete paradigm shift for the US or for any region for that matter. But forgetting about that discussion, if we commit to the tunnel, then we've committed to the construction of an E plus E minus factory way before 2030. So these things, which are reality and the questions which are there, we need to openly discuss it. And going to the ITF report, then which says 0 to 2 years for preparation and less than 12 years to physics. If Japan, with some miracle, says in the next year or two, we are going ahead, then this timeline is compatible with that. Now, if that ITF report is not compatible with the pre-lab timescale, I'd suggest the Accelerator Frontier to look at that.
Okay, can I also add a bit more to what Tor said?
Speaker first. Yep.
So apart from what ITF did, but talking to also with Japanese counterparts, my understanding there's maybe a requirement of a pre-lab before we reach a pre-lab about 4 years time scale roughly, and then the pre-lab stage before the final commitment another 4 years. So in principle, within 10 years, you can have a full approval, and then you can do also in parallel the necessary R&D to bring it into actual construction and production. So I think it's compatible with this time scale. Of course, going back to also the previous question, the US have a strong say in this, strong contribution, and not only US, but international community. So it's not just we're waiting for Japanese to tell us if they go ahead or not. The Japanese are also waiting for the international community to commit. So it's a dual relationship that has to move forward. And it's not just one partner, many international partners. So this is part of the discussion that has to happen now if you want to have, say, an ILC in Japan within 10 years. And I think it's compatible with this timescale.
Okay, we have one more comment here.
Sorry, I'd like to amplify my previous 3 comments. First of all, CERN has taught us that you need a big tunnel, and it's very natural, almost obvious, that the first thing to put it in is E+, E-, i.e. Higgs factory. Accelerator physicists really only know how to do one thing, and that's build circular accelerators.
At the large scale.
Well, that we will hear in the next topic, but look, they built linear as well.
The SSC has taught us that you cannot do research at the billion-dollar funding level, because in the US, it's because every congressperson, every senator becomes an accelerator physicist, and you can't do it. It's impossible.
But we have at least
So
one.
This comment, I regret to say, applies also to the ILC. The ILC can't realistically succeed because there's just too many uncertainties. The big tunnel in Illinois also has uncertainties, but they're way, way less than every other uncertainty.
Thank you for your comment. So I'm looking for the can. Look, maybe do you have a mic? No. One more because we have to move.
I guess the nice thing about Snowmass is that we have all the different frontiers here. How aligned is this with what we're going to hear from the other frontiers? And specifically, is there a concern that from the energy frontier standpoint, we'd all love to move forward with a Higgs factory on the 2030 timescale, but is there another chunk of the community that's going to say, no, we've just spent $3 billion for a neutrino program, and let's double down and go to 2.4 megawatts in that same time frame, and then we're going to leave it to P5 to hash all this out, or has this already been kind of worked out?
You answered your question. P5. So look, we have to move on. Sorry, guys, because we really have to let sort of.
But it's a very good question.
Yeah. So while we are sort of,
We can
thank you
ask-
very
yeah,
much.
thank
Look, let's applaud. Yeah. So.